Once again, very good day to everybody. This is machine learning. Okay, and this class we discuss about the linear regression techniques. Okay, so this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. In this class, we'll have a short introduction towards linear regression technique, how you try to train the model, what are the cost function that is associated with this linear regression. Then we discuss about the scatter plot technique. Okay. Then we find the total residual error that is associated. Then we have the Python implementation of this technique on a small data set. What is the response vector that was associated? What is the linear response model? Okay, as matrices that we'll discuss. Finally, we discuss with the least squares method. Okay, so I had already given the independent work for you. Please complete them. I will check them. And at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. Right. So linear regression is based on, like in the case of neural networks, we have supervised and then unsupervised reinforcement. We have several learning algorithms. So here linear regression is based on supervised learning. It is performing a regression task. Okay. So here the target prediction value is actually got from the independent variables. Like we'll have several variables that are independent. Okay. And we'll try to understand the relationship between the variables as well as the forecast. So here there are two types of variables. One is dependent variable and another one is independent variables. And our regression models will be focusing on how you try to understand the relationship between the dependent as well as independent variables, and we will be using more about the independent variables in order to better analyze the regression technique. Okay. So here the linear regression is all about predicting a dependent variable, okay, that is nothing but y, based on an independent variable which is nothing but x. So dependent based on independent. Okay. So this is the linear regression with respect to x and then y. We'll have a slope. Okay. So we'll identify several points between the dependent as well as independent. Okay. So here we'll find out the relationship. As I told you, relationship is thought between x and y. Okay. So here we call it as a linear regression, which means that x is nothing but the input, nothing but the work experience, and y is nothing but the salary of the person. Okay. X input, y oil. Okay. Right. So the regression line is the best fit line. We'll identify a hypothesis like y is equal to theta 1 plus x into theta 2, x multiplied by theta 2. So when training the model, as I told you, x is nothing but the input training data that you are giving. Okay, it's a univariate function. It is a one input variable. Okay, it is based on the parameters, while y is nothing but the label to the data, like what you call to be the supervised learning. As in the beginning of the class, I told you, it is based on supervised learning. So when you train the model, it fits the best line, okay, to predict the value of y based on the value of x. Okay, so the model will be getting the best regression fit line by finding theta 1 and theta 2. Theta 1 is nothing but the intercept and theta 2 is nothing but the coefficient of the x value. Okay, so when you find theta 1 and theta 2, we will find the best fit line. Okay, so you can finally use the model for prediction for the value of y based on the value of x. So here we identify the cost function like j. Okay, so in order to find out the best fit regression line, you are going to predict the value of y based on the value of x. So what you have to do, you have to update the value of theta 1 and theta 2, like maybe y value is the predicted value and true value that is actually y. Okay, so minimize is equal to the 1 by n, okay, summation I equal to 1 to n predicted of I minus yi the whole square. So that is actually the summation of prediction minus y the whole square. So j is equal to, we are going to have 1 by n summation I equal to 1 to n prediction minus y, that's actually prediction for I minus yi the whole square. Okay, so here the cost function is nothing but the root mean square, okay, root mean square error between the predicted y value and the true y value. Okay. And here, in order to reduce the cost function, we can go with the gradient descent method. Already we discussed about gradient descent method. So the same thing we will go. We will try to update the values of theta 1 and theta 2 in order to reduce the cost function, in order to reduce the root mean square, okay, evaluation. Okay. So if you do this one, you can achieve the best fit line, and of course you can use the gradient descent. Okay. So you have to update the values of theta 1 and theta 2, and you have to iterate the value, okay, so that the minimum cost is actually reached. Okay, so here is the Python implementation. First of all, we will try to understand, okay, the concept. Okay, the simple linear regression you can identify to predict a response using a single feature, and here two variables are linearly related. Linearly related means like the output will be following the input. Okay, that is linear. Okay. So we will find out a linear function that is going to predict the response value y, okay, as accurately as possible as a function of feature or maybe independent variable x. Okay, so maybe you will have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and corresponding to that we will have the values 1, 3, 2, 5, 7, and so on. Okay, so you are going to linearly predict the output. Okay, this is the actually the scatter plot, like x, the input vector, feature vector, like x1, x2, x3 up to xn, and similarly y is nothing but the response vector, y1, y2, y3 up to yn. This is for the n observations, for example like 10 observations. Okay, so here we are going to plot x versus y, so it will go like this. Okay, like this it will go. Okay, so this is nothing but the scatter plot, x versus y. Right. So now next what you have to do, you have to find out the line, the best fit line for the above scatter plot. Okay, so that we can predict the response for the new feature values. So this line, whatever you are joining, will be the regression line. Okay, so here the regression line will be having hxi, which is nothing but the predicted response value for the ith observation, and then b0, b1 are nothing but the regression coefficients, and they will be having like y-intercept, okay, and the slope of the regression line. And in order to create the model, we should first of all learn the model. You should be able to train the model according to the regression coefficients b0 and b1, and once you have estimated this one, we can use the model to predict the responses. So these are the mathematical equations that are associated. We will have yi, okay, yi, the response vector for the ith observation. It is nothing but beta 0 plus beta 1. Okay, b0 plus b1. Okay, xi plus epsilon I equal to h of xi plus epsilon I. So this one, it will be corresponding to epsilon I, okay, which is equal to this. If you can take this h of xi, if you take here, it will become yi minus h of xi. Okay, right. So this ei or maybe epsilon I is nothing but the residual error in the ith observation. Okay, so you have to actually reduce or maybe minimize this total residual error, and for this one you will be calculating the total cost function. So j of beta 0 comma beta 1 equal to 1 by 2 n summation I equal to 1 to n epsilon I square. This is actually the root mean square error value. Okay, right. So this the task is to find the value of this beta 0 or maybe b0, b1, for which the value, the cost function is actually minimum. The cost function is actually j of beta 0 comma beta 1 is actually minimum. Okay, so next we have to go with finding the beta 1 and beta 2, I mean beta 1 and beta 0. So sxy, sxx. Okay, the beta 0 is equal to y minus beta 1x. So actually this one is nothing but the sum of cross deviation of x and y. So sxy equal to summation I equal to 1 to n xi minus x bar. This is actually the mean value. X bar is nothing but the mean. Okay, it multiply by yi minus y bar. So y bar is nothing but the mean value. Okay, which is equal to summation I equal to 1 to n yixi. Okay, so this one you are multiplying yixi minus n x bar y bar. So here sxx is nothing but the sum of the square deviations. Okay, so sxx is equal to summation I equal to 1 to n xi minus x bar the whole square, which is also can be taken as xi square minus the n function, the total n function multiplied by x bar the whole square. Okay. So this is the Python implementation for the above technique. So import numpy model as npy, import the matplotlib.pyplot as plt. So define, estimate the coefficient of function x and y. Okay. So here you are finding the number of observations or maybe the number of points. Okay. So n is equal to np.size of x, and you are finding the mean or maybe average of the x vector and y vector. So mx is equal to np.mean of x, my is equal to np.mean of y, and you calculate the cross deviation and the deviation about x. So yes, xy equal to np dot sum yx minus nm ymx. So that previous thing only we are taking this one. Okay. And yes, xx is equal to np dot sum xx minus nmx multiplied by mx. Okay. And you find out the regression coefficients. Here the regression coefficients are nothing but b1 and b0. So b1 is equal to ssxy divided by ssxx, and b0 is equal to my minus b1 multiplied by mx. Okay. And you return b0 and b1, the regression coefficients, and define plot regression line x, y, and b. Okay. So it is nothing but the input, response, and then regression factors. Okay. And then plot the actual points as a scatter plot. plt.scatter x, y, color equal to m, marker equal to 0, and s is equal to 30. Okay. And then you'll have predicted response vector. So y predict is equal to b0 plus b1 multiplied by x, and you plot the regression line. So the plot you'll have, okay, x, y predict, color equal to g. So color g means it's actually green color you are going to point out. Okay. And you put the labels plt.x label of x, plt.y label of y. Okay. And you have the function to show the plot. It is actually plt.show. Okay. And you define the main function x is equal to numpy.array 0, 1, 2, 3, 4, 5 up to 9, and then y equal to np dot array 1, 3, 2, 5, 7, 8, 8, 9, 10, 11. This is actually got from this one. Okay, this function only we are getting. Okay. Okay, and then you estimate the coefficients. B equal to estimate coefficient of x comma y, and you print estimated coefficient is equal to nb0, nb1. You will try to print it in the format, and you plot the regression line x, y, and b. And if the name is equal to main function, then you will have the output. Okay, so b0 the estimated regression coefficient, and b1 the value. And similarly, we had the already scatter plot like this one. So with this, it will be creating a slope of the green color because you specified g. Okay. And then you'll have multiple linear regression also. So we'll model the relationship between multiple features, between two or more features. So it's nothing but an extension of the simple linear regression. So here we'll be having a data set with p features and maybe one response or maybe dependent variable. Okay. So here the data set will be having n rows or maybe n observations, and we define the feature matrix to be a matrix of size n cross p. Okay. So here x is nothing but xij is nothing but the value of the ij. Okay, I mean the jth feature for the ith observation. So definitely your factor will be x11, x12 up to x1p, x21, x22 up to x2p, x31, x32 up to x3p, and similarly xn1, xn2 up to xnp. And similarly response vector will be having the vector of size n, where yi is nothing but the value of the response for the ith observation. So it will be a column vector. Okay, y1, y2, y3 up to yn. Okay. So here the regression line would be, okay, h of x equal to beta 0 plus beta 1 of x1 xi1 plus beta 2 xi2 plus beta 3 xi3 up to beta p xip. And here this xi is nothing but the predicted response value for the ith observation. b0, b1 are nothing but the regression coefficients, which we already discussed. Okay. And then we'll have yi is equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 up to beta p xip plus epsilon I. Okay, so this is actually the residual error. Okay, what we discussed. And then or maybe yi equal to h of xi plus epsilon I. This is what we actually derived from the previous relation. Okay, so this one. or maybe you can also write yi minus hixi is equal to epsilon I. Okay, so this is the residual error of the ith observation. Okay, so you can categorize the linear model also based on the feature matrix like 1 1 1 1 x11 x12 x13 up to x13 x21 x22 x23 up to x2p. Similarly xn1 xn2 xn3 up to xn. Okay, and similarly your y function would be x beta plus epsilon. Okay, you know beta the the regression values. Okay, and epsilon is nothing but the residual error. Okay, so beta is equal to column vector beta 0 beta 1 beta 2 up to beta n, and similarly epsilon is also a column vector epsilon 1 epsilon 2 epsilon 3 up to epsilon n. So finally we are going to have with the least square method. So you have to estimate b. So maybe b or maybe b dash. Okay, so that can be estimated using the least square method. Here you can minimize the total residual error. So for this one, b cap is equal to x dash x inverse x dash y. Okay, so that is nothing but that dash is nothing but the transpose of a matrix. For example, if you have like this one, okay, it will be changing like this one. Okay, so that is the transpose of the matrix, and similarly something to the power of minus 1 here, this one x dash x to the power minus 1, it is actually inverse. Okay, so when you know the least square estimates, okay, beta dash, then definitely your multiple linear regression model can be estimated. So y cap is equal to x multiplied by beta cap. So here y cap or maybe y dash is nothing but the estimated response vector. Something which has cap means it is estimated.